kind of general talk on analysis on arithmetic manifolds. All right. So let me start with somehow the basic setup. We give ourselves a Riemannian manifold, and it comes with a Laplace operator. And the natural thing to look at is eigenfunctions of the Laplace operator. So we have an eigenfunction f, that's an eigenfunction of the Laplace operator, and we normalize it in a way that the total mass is 1. And the basic question is, how is the mass of S distributed on my manifold? If I have a fixed function, then f is whatever it is, but I want to look at this asymptotically as the eigenvalue goes to infinity. And then I have a sequence of functions, and I would like to know, is the mass somehow equidistributed, or are there big peaks, or what can I say about this? And one could maybe naively hope that there is some sort of equidistribution. The larger lambda becomes, the more equidistributed the mass should be. Okay, this is not a very precise statement, and we should first clarify what I mean by equidistribution. And there are several ways to view this. The first interpretation would be, I take my eigenfunction f and take the square and integrate it against some other function. And that should be roughly the same as if I integrate a constant against my favorite test function. That would be equidistribution in a weak star sense. And this is what is usually called quantum unique ergodicity, a very famous problem. If all Laplace eigenfunctions satisfy this as the eigenvalue goes to infinity, then we talk about quantum unique ergodicity. And this has some background in quantum physics, which I don't want to go into in much detail, but this is something that the physicists are interested in. The second interpretation would be as follows. We have our big manifold X, and we can restrict the eigenfunction to an interesting submanifold, say X0. And well, you could ask, is the portion of the mass of F on X0 roughly of the expected size as compared to X? The bad case would be if F accumulates a lot of its mass, let's say on a geodesic or some other interesting submanifold. Okay, and a special case of this in some sense is if the submanifold is just a point and you want to have upper bounds, let's say for the sup-norm or for some other LP norm. And if the 2 norm is fixed, then a large P norm tells you that there must be peaks, whereas a small P norm tells you that there cannot be clusters of mass. Yeah? So there are many ways to measure in what sense an eigenfunction can be equidistributed. All right, let's look at a few examples. Let's start with the simplest possible situation. We take just a torus. So you take r to the n and mod out by a lattice. This gives you a torus. Okay, the Laplace operator is what it is. And we can write down the eigenfunctions very explicitly. They are just exponentials parametrized by the dual of the lattice. Okay, and the eigenvalue is given essentially by the norm square of that element. All right, well, there is not much to say because obviously the absolute value of this is just the normalizing factor, 1 over the square root of the volume. And so there is perfect equidistribution. There's nothing we can say about that. I mean, this is just an optimal case, and that's the end of the story. Well, it's not the end of the story, because these are eigenfunctions, but it's not clear if they are all eigenfunctions. It could be that the dimension of such an eigenspace is large. And then if you have a large eigenspace, there are many ways to cook up a basis. And okay, I've written down one basis, but you can choose a different basis. And simply by linear algebra, if you just cook up a nice linear combination, you can, I mean, if you have a big eigenspace, you can do whatever you want. In particular, you can arrange that the mass is badly distributed. Here is an example. just take n equals 2, a two-dimensional torus, take as a lattice just the integers, volume is 1. And here are two vectors of length 65. And now if I take a certain linear combination, then here you see that the eigenfunction is still L2 normalized, but the mass is not at all the same all the time, but there are peaks and so on. However, there is another however. This is not kind of a natural eigenfunction. The point is that there are more operators, not only the Laplacian, but there are more operators. And it's very reasonable to choose a specific basis, namely a basis where you have joint eigenfunctions of all shift invariant operators. And those eigenfunctions are just these functions here, and they have perfect equidistribution. So what do we learn from this slide? We learn A, that if we have a large eigenspace, everything can happen. But B, it would be clever and also reasonable to choose a basis that is not only eigenfunctions of the Laplacian, but eigenfunctions of all shift invariant operators. And this basis should be well behaved. That's the moral of the story, and this will come up over and over again in my talk. Okay, here's a second example, only pictures, no formulas, no mathematics. This is the stadium. And here you see heat plots of eigenfunctions. I forget what is what. Either red is big and blue is small, or the other way around. But you see, there are eigenfunctions that are not at all equidistributed, but they show, here you see, they show certain parts where things are bigger and smaller. And yeah, this features certain symmetries of this stadium. Yeah, so eigenfunctions can behave in a very interesting way. That's what you should learn from this slide and from these pictures. Okay, third example. Let's take the sphere. This is now 18th century mathematics, 200 years old, and we can compute everything totally explicitly. We choose polar coordinates on the sphere, so we have two angles, theta and phi. And we parameterize everything by theta and phi. And the Laplacian is given in this way. And we can compute the eigenvalues simply by solving a differential equation. And the eigenvalues are parameterized by numbers k times k plus 1. And again, we are in the situation where the eigenspace is big. The larger k becomes, the larger our eigenspace is, namely it has dimension 2k plus 1. Okay. We can write down a basis of eigenfunctions, and these are the so-called spherical harmonics. It's not so important what they look like, but you can write it down. And basically, they are made out of general Legendre polynomials. They are Legendre polynomials in terms of the angle theta and exponentials in terms of the angle phi. And there is some normalization. Okay. Okay, so we can write down everything very explicitly, but it's important to have a more conceptual interpretation of this. And it's important to view this as a representation theoretic problem. Now, as is well known, we can characterize the irreducible representations of SO3. For each odd number, there is a unique representation of degree 2k plus 1. And so it occurs with dimension, with multiplicity, 2k plus 1 in the L2 space of SO3. Okay, and of course, by Schur's lemma, since it's an irreducible representation, the invariant Laplacian acts as a scalar on each of these representations. Okay, and in each of these representations, which is a 2k plus 1 dimensional vector space, there is one vector that's SO2 invariant, and that's the so-called spherical vector. And this, so SO3 modulo SO2 is just the sphere, and these are the eigenfunctions on the sphere. Okay, and so since, yeah, so I get 2k plus 1 for each k, I get, because it occurs with multiplicity 2k plus 1. I get 2k plus 1 eigenfunctions, and these are the spherical harmonics that we saw on the last slide. And here are some pictures of these Legendre polynomials. So you remember we had this Legendre polynomial here. And for now, I take m equal to 0. I just look at pk. No. In fact, I take k to be 30 and I let m run. But I restrict to angle phi equal to 0 and look at this only in terms of theta. And you see if m is 0, then you have a polynomial that's big outside and very small inside. And the larger m becomes, the more the mass tends towards the middle. And so here in the end, you have no oscillation whatsoever, but you have a peak in the middle. And here you see the three-dimensional version. So this is now the sphere with a heat plot. Here you see for m equals 0, you get a big heat on top, and then it oscillates in the middle. And the bigger m becomes, the smaller the value is outside, and then you get the heat inside, right? Okay, so this is what the eigenfunctions look like. All right. So far, there was no number theory whatsoever. This was just analysis on manifolds. And let me continue a little bit and focus on the problem that I'm actually interested in. This is the sup-norm problem. So I take, what I'm interested in is the sup-norm of such an eigenfunction. So pointwise bounds for L2 normalized Laplace eigenfunctions. And again, if I get a good bound, it means that the mass is kind of equidistributed. And there's a general theorem that is a purely analytic theorem that tells you that the sup-norm is bounded by a constant times lambda to the power dimension of your manifold minus 1 divided by 4. In particular, for a surface, if the dimension is 2, then it's 2 minus 1 over 4 is lambda to the 1/4. And this is in fact sharp. If you look at the 2 sphere and take your Legendre polynomial, then the eigenspace, so the eigenvalue is k times k plus 1. So this is lambda to the 1/4, and this is sharp. And the reason why this blows up with lambda, at least like lambda to the 1/4, is again, we have a large eigenspace. And so a large eigenspace can lead to a large sup-norm. We have seen this a few slides before. Okay, so we have a general bound and we see it's sharp. So that's the end of the story. But it's not the end of the story, because I want to talk on something that has to do with number theory. And let me now introduce the concept of an arithmetic manifold. An arithmetic manifold is a manifold that's not only a Riemannian manifold, but it also has Hecke operators acting on the manifold. So there are more operators than just the Laplacian, namely arithmetically defined operators. And I call them Tn, and they are parametrized by natural numbers that act on the manifold, and they should be normal so that I can diagonalize with respect to these operators. And now I don't look at arbitrary eigenfunctions, but at joint eigenfunctions, eigenfunctions that are both eigenfunctions of the Laplacian and these Hecke operators. And then there is a hope that these joint eigenspaces should be one-dimensional, and then the problem becomes interesting. Maybe in this case, we can prove good sup-norm bounds. Okay, let's look back at our favorite example, namely the sphere. What are these Hecke operators on the sphere? Now, they are given as follows. You take integral Hamiltonian quaternions, x plus iy plus jz plus kw, of norm n. And you call this Rn. And you view this as a matrix in SU2, and SU2 is essentially the same as SO3. And now each Hamilton quaternion gives you a matrix in SO3, and you can compose your function f with all those matrices modulo units. Okay, this would be a Hecke operator, a very naturally defined Hecke operator on the sphere. Example 2 is maybe the most classical one. You take the modular curve, SL2R modulo SL2Z modulo SO2, upper half plane modulo SL2Z. And here, the role of the Hamiltonians is played by the matrix algebra, by the 2x2 matrix algebra. And you take matrices with determinant n and compose those with your function. That's the usual Hecke operator. And you can generalize this example, and you can view, or you can work with an arbitrary locally symmetric space, G mod K, modulo an arithmetic lattice gamma. And you can define in a very similar way Hecke operators and get an arithmetic manifold, and you can consider joint eigenfunctions. These joint eigenfunctions they enjoy very beautiful properties, and they have been subject to intensive studies. And let me show you two landmark results. One is the famous Ivanets-Sarnak result from the Annals in 95 for sup-norm bounds. You remember the trivial bound is lambda to the 1/4. But once you consider joint eigenfunctions, you can save a little bit. Okay. And the other famous result that gave a Fields Medal to Lindenstrauss is not quantum unique ergodicity, but arithmetic quantum unique ergodicity. So not for all eigenfunctions, but for joint eigenfunctions, we have this quantum unique ergodicity formula. So you see that, yeah, joint eigenfunctions enjoy very nice features that can be the subject of very nice theorems. Okay, but still maybe some more motivation. Why should we at all care about sup-norms? What is interesting, or what are the applications of knowing that joint eigenfunctions have a small sup-norm? Let me give you some applications. The first application is Ivanets-Sarnak's original paper and gives you applications to subconvex bounds for L functions. And indeed, their result essentially gives, well, maybe not quite that, but something very closely related to this, a sup-norm bound for the Riemann-Zeta function. The convexity bound on the half line would be 1 plus t to the 1/4, and you can save 1/24. Second example is more of geometric nature, the growth of nodal domains. Take a joint eigenfunctions on the modular curve and look at the zero curves. So if you have your modular curve and your eigenfunction gives you certain curves where the function is 0. And so this partitions your modular curve into connected components. And you can ask, how many connected components are there as the eigenvalue grows? And having a good sup-norm available can be used to prove that the number of connected components, the number of nodal domains, goes to infinity as the eigenvalue goes to infinity. Very interesting application and needs a sup-norm bound. Here's the holomorphic analog. If you take holomorphic Hecke eigenforms of weight k, then of course, because it's holomorphic, the zeros are just points, not curves. And we know that once the weight increases, there are about k/12 zeros. So there are more and more zeros. They get denser and denser on the modular curve. And it turns out that they are equidistributed. They are not just random points, they are equidistributed. And this needs at least a weak sup-norm bound. Not a very strong one, but it needs some weak sup-norm bound. That's a theorem of Seyffarth-Nick. And finally, something from algebraic geometry. There is something called Falting's delta function. And this is a height function on an algebraic variety defined in terms of a metrized line bundle. And it's used in his proof of the famous Mordell conjecture, for which he received the Fields Medal. And okay, you may ask what happens if you take congruence covers. What happens with this height function? And Jorgensen and Kramer provide uniform bounds. And this also needs sup-norm bounds, at least on average over a certain family. So what I'm trying to say is that these sup-norm bounds enter in many situations. And so maybe it's useful to have such bounds available. All right. Okay, and if you're still not convinced that this is something interesting, here is a recent screenshot from MathSciNet where I've just plugged in the word sup-norm. I don't know why some of them are highlighted and some of them are not, but you see there are many papers that have sup-norm in the title. And so this is a very active area of research. All right. So now let's do a little bit of mathematics. I've done enough advertisement for sup-norm bounds. So how do you actually prove something? And okay, how do you? Okay, here is the only actual proof in this talk, and it's a very beautiful toy problem that I learned from my friend Gergely Hartsosh. And suppose you are given the function sine x plus cosine x. What's the sup-norm of this function? Okay, the trivial bound is 2, because both sine and cosine cannot be bigger than 1. But of course, if sine is big, then cosine is small. So 2 is too bad. You should be able to do better. And the correct sup-norm bound is square root of 2. Okay, obviously, all of you can prove this in 2 minutes, maybe less. But here's a very short half-line proof. Okay. First, we square this, sine x plus cosine x squared. And now comes the main step. We artificially add something. In this way, we only make it bigger if we add a positive number. But now, if you compute this, this equals 2 on the nose. And now you drop this term, take square roots, and you're done. Okay, what do we learn from this example? The first lesson we learn is don't use calculus. Second lesson we learn is it's good to embed things into a bigger family. Don't look at this function by itself. Look at this function together with some other function. And embed it into a bigger family, and then you have a chance that in this family, you have much better structural properties. Okay, here's the general scheme. Suppose you want to bound the sup-norm of something, then it's the supremum over all z of this function, but you don't look at this function by itself, but rather within a family. Of course, you need to choose this family cleverly, and there's a loss because you add some stuff, but maybe this loss is controllable. This by itself is not yet enough. It only works in this toy example. You need another trick. You need to weight this average in your favor. I mean, this is lossy, but the function you're interested in, you want to amplify with a big weight, and the other functions that you just add for fun, that you want to amplify with a small weight. Okay? All right, that's the general strategy. And the hope is that this spectrally complete sum can be evaluated more easily, just as in this toy example. Okay, this can be made precise by what is called the so-called pretrace formula. And I show this in some generality. So the idea is we take our locally symmetric space, G mod K mod gamma, and we take a function that's by K invariant. And then we look at the following average. We sum K over Y inverse gamma X, where gamma runs over gamma. And you see with bare eyes that this function is in both variables, left gamma and right K invariant, because K is by K invariant. So you can change X and Y from the right by K, and you can change it from the left by gamma, because this is eaten up by this gamma sum in the middle. Yeah, so it's clear that this is a function on X times X. Now, the space X has a spectral decomposition, and you can decompose this function kappa with respect to both spaces, and you get a spectral decomposition. Okay, and a non-trivial computation that goes back to Selberg gives you a sum over eigenfunctions weighted by a function h that depends on k, and that depends on the so-called spectral parameter. So each fj is an eigenfunction of all G invariant differential operators. This includes the Laplacian, but some more. And this is an algebra, a finitely generated algebra, and you get a tuple of numbers that can be viewed as elements in the dual Lie algebra. And this function h depends on this tuple. And this function h can be computed in terms of the original function k as the so-called spherical transform. You need to integrate it against the so-called elementary spherical function, and the elementary spherical function is this. You can view this as the Fourier transform on the group G. And indeed, in the special case where G is R and gamma is just the integers, if you have the torus, if your space is the torus, then this is the Fourier series. Yeah? But this is kind of a non-commutative way of a Fourier series if the group G is non-commutative. Yeah, for instance, SL, N, R, or something like that. Okay, so this is a way, so here you have a sum over gamma over your group, and you can transform this into a spectral sum. And that's called the pretrace formula. And here it's again, if you plug in x and x, you have on the one hand the geometric sum, and on the other hand, the spectral sum. Okay, and if it happens that this weight h is non-negative, then you get a lower bound by dropping all but one term. All right. And now we use, at this point, we use the fact that we have an arithmetic manifold because we can use our Hecke operators. And if we plug in these Hecke operators, we can cook up a weight by combining the Hecke eigenvalues in a clever way. This is a somewhat technical construction that I don't want to go into in detail, but you can use the Hecke eigenvalues to cook up your amplification weight. Okay, and at this point, you use crucially the fact that it's Hecke eigenfunctions that you're considering. All right, yeah, as I said, this can be used to create an amplifier. All right, so this is the setup in kind of in a nutshell, and let me tell you what ingredients are necessary. First of all, we need a spectral decomposition, and phrased in representation theoretic language, it's classification of irreducible representations. Secondly, we need to have a good test function h, which is non-negative on the spectral side, which picks up enough that I have a good family, but not too much so that the family is not too big and we don't lose too much. Okay. Then we need to construct the amplifier in terms of our Hecke eigenvalues. And yeah, what is the actual meaning of this is that somehow there is a local global principle. We want to localize not only at the Archimedean place, but also at p-adic places. And if we localize at sufficiently many places, we get a good understanding of our family. And so you can view this as some sort of local global principle. Okay, and the actual construction of this amplifier needs the Hecke relations. It needs the properties of the Hecke algebra. And this is rather simple in groups like SL2, but if you take complicated groups, then Hecke algebras are rather complicated from a combinatorial point of view, and some non-trivial algebraic combinatorics is needed. Then you need to analyze the spherical transform. So you remember from the previous slide, this h depends on k. Here is the spherical transform. Yeah, and if you give yourself a function h, then you want to know what is k, or vice versa. And this is rather difficult. I mean, okay, this is like a Fourier transform, but in this general context, it's very complicated to compute what this actually is. So you need to understand this spherical transform. And this has to do with asymptotics of spherical functions and analysis of integral transforms. So it's analysis on Lie groups. You have your special functions that are attached to a Lie group, and you want to know the asymptotics. And finally, you need to count matrices. So again, if you look at this slide, your function k has a certain support, and you want to know how many matrices satisfy that x inverse gamma x are in the support of k. So this gives an actual number theoretic problem. You need to count matrices in certain ranges with certain constraints. Okay, and finally, okay, so this needs geometry of numbers and some Diophantine approximation. So this is something purely number theoretical. So this is close to my heart because this is where we can do actual number theory. And finally, if X is not compact, we also have to take care of the continuous spectrum, not only the discrete spectrum, and this requires some extra technical arguments. All right, let me show you two of these points, namely asymptotics of spherical functions and some counting problems in slightly more detail to give you a flavor what this actually involves in practice. What do you need to do in order to prove something? So let me start with the analysis part. We write our group in Iwasawa form, and we project down to the A component, and then we also project to the Lie algebra of A. And the spherical function is given in this way. So the spherical function is an integration over the compact part. And of course, this function by construction is by k invariant. So you only care about g modulo k on both sides. Okay, and this is the formula. Okay, that's what it is. But this is not very practical in terms of computations. I mean, how do you compute this? Give yourself a t and give yourself a g. What is this? And how can you bound this? Let's look at the simplest example of the group SL2R. Then this function is a well-known function. It's a Gauss hypergeometric function that has been studied in the 19th century. And so we basically know everything about this function that we want to know. Just look at tables of special functions, and you find everything about Gauss hypergeometric functions. However, in general, for other groups, we've absolutely no idea what that spherical function is in terms of known functions. These functions have never been studied. So these are some special functions, but there are no tables or integral transforms or anything that you could look up. So you need an abstract argument. And one theorem that I want to present is something that I proved some time ago with Anke Pohl. And we proved that the spherical function decays both and uniformly in terms of t and in terms of h. So if t is 0, okay, then there is nothing we can say here. And if h is the identity, there is also nothing we can say. But if either h goes a little bit away from the identity or t goes a little bit away from 0, then we get some decay. It's measured in terms of the product of the two norms. And the feature is that this is completely uniform in everything. Yeah. So as soon as the product t times h goes a little bit to infinity, we have already decay. Yeah. This is the crucial statement here. So that's one theorem I want to mention. And this uses analysis on Lie groups and a good understanding of, well, you somehow have to understand how this spherical function works. Yeah. So as I said, the key feature is uniformity in both t and h, but of course there have been many other results that have stronger exponents but are less uniform. Okay, Let me now turn to number theory. And if you want to bound sup-norm bounds on GLN, here is a sample number theoretic problem. Give yourself a fixed positive definite matrix Q, a large parameter L, and two primes P and Q roughly of size L. And the problem you have to solve is the following. Count all matrices such that they are almost orthogonal with respect to Q, in the sense that gamma transposed Q gamma is essentially Q up to a very small error. Think of L as being big, then you have a very small error. So they are essentially orthogonal with respect to Q. And the determinant is Q times P to the n minus 1, where Q and P are your primes. And this is the trickiest condition. The GCD of all 2 by 2 minors of this matrix gamma is P. Okay. And the target is you need to show that there are at most L to the n minus 1 minus a little bit of such matrices. It's a difficult problem. Okay, how could you prove this? Okay, we first choose the first column of gamma randomly. How many choices are there? There are n entries, and they are all of size at most L, because of this determinant condition. The determinant is roughly L to the n, and so each entry is roughly of size L. There are n entries, but they have to satisfy a quadratic equation. So we get L to the n minus 2 choices for the first column. Now the first column is fixed, and what is left? Well, we have L to the n minus 2, and our target is L to the n minus 1 minus delta. So there's almost nothing left. So everything else has to be determined by fixing the first column. And the only available condition that we have not yet used is this condition. And indeed, one can show that using this condition, but this requires number theoretical work, that this condition fixes everything else. Once the first column is fixed, by this condition, everything else must be fixed, and so we win. But this is a hard number theoretical problem, but it's fun. I mean, this is really number theory. All right, this is the classical sup-norm problem, and I want to use the remaining time of my talk, and let me quickly check how much time I have left. Okay, there is quite a bit of time left. Okay, so let me use the last 10 minutes to show you new directions in the sup-norm problems. What I've presented up until now is the classical approach and the classical theory. And let me now look at more modern and new directions. So the classical sup-norm problem, as we discussed it, looks at bounds for eigenfunctions on G mod K mod gamma on a locally symmetric space. Okay. It's equally natural to look at this on the group level. So nobody forces us to mod out by K on the right. We can just look at eigenfunctions on G mod gamma. Yeah, we don't have to mod out by K. The problem makes just as much sense. So let's see what this means in practice. Let's take the most classical example of the group SL2R, which you, if you like, you can think of this as SO21. Okay. Our maximal compact is abelian. So modding out by K doesn't mean much because we only mod out by an abelian group. So the representations are all one-dimensional. So I don't have interesting representations of K. They are all one-dimensional. Yeah, so all its representations are just what we call the weights. They are one-dimensional and not much is going to happen. And of course, you can look at eigenfunctions of high weight And this has been studied by many people, and this is a classical problem. Okay, so nothing interesting, or nothing, a lot of interesting facts, but nothing new can be said in this example. So let's look at the first situation where K is not a billion. Let's take SL2C. Now the maximal compact is SO3, roughly, or SU2, and it's non-abelian. And that's the group we looked at earlier, a few slides before, and we studied the representation theory of K. And as you remember, for each odd integer, there is a representation of dimension 2k plus 1. So the dimension grows and grows and grows as k goes to infinity. Okay, so these are the representations of k, but we can also parameterize the representations of g. And irreducible representations of G mod gamma are parameterized by pairs nu and p. Nu is a complex parameter, p is an integer. And the representation space decomposes in this way. Each v decomposes into vk, where k is at least p. And then each vk decomposes as VKM. And I will explain this VKM in a moment. So these VKs are the 2k plus 1 dimensional spaces. And this decomposition is a decomposition with respect to the diagonal matrices. We'll see this on the next slide, or maybe later at least. This is the so-called Wigner basis. If you happen to be a physicist, then you are very used to this kind of thing. If you're not a physicist, don't worry. But yeah, so this is a very natural decomposition that I will describe in a moment. The most interesting case is the lowest weight situation where k equals p. This is maybe related. So in the classical example, you would maybe take mass operators to artificially move up and down the weight, but the most classical situation is the lowest weight situation. So let's look at this situation where k equals p. Okay, and so in this space k, is there a question?
No.
No. Okay, so if in this space, okay, so I hear an echo, but or I hear something. Okay, let me continue. So in this space Vk, which is 2k plus 1 dimensional, we can choose an orthonormal basis. And so we get a vector valued. This is now a different situation. We get a vector valued function that transforms with respect to k in k on the right with respect to that representation, that 2k plus 1 dimensional representation. Okay, so once your representations are not one dimensional, you basically look at vector valued automorphic forms. That's the lesson you learned from this slide. And so the sup-norm problem now becomes a problem of vector valued automorphic forms. Okay, let's be concrete. Let's choose maybe the most natural lattice in SL2C, the lattice that comes from the Gaussian integers. You could take a different arithmetic lattice, but that's maybe a nice one and a very concrete one. Okay, and what I'm now interested in is the sup-norm problem in the dimension aspect. So I want to estimate this vector valued automorphic form as the dimension of the vector grows. Okay, so for technical reasons, we fix an omega, so we fix a compact set, omega in G, and we also fix a spectral parameter nu, and we are interested in what happens if k grows. So if the dimension of my representation grows, and I take, well, what do? I take the 2 norm of this vector. It's a 2k plus 1 dimensional vector. And the trivial bound would be k to the 3 over 2. Okay? I'm not going to explain why this is the trivial bound, but that is what you can very easily prove by basically doing nothing. This follows from abstract nonsense. Okay, and the theorem that I want to present is joint work with my friends and colleagues Gergely Hartsosh, Peter Maga, and Georgi Milicevic. And we proved, well, half a year ago, that you can actually save a little bit. The trivial bound is k to the 3/2, and you can save 1/6. Okay. That's the first theorem that I want to present. And the second theorem is, okay, now this is about a vector of forms, and you bound the 2-norm of this vector. Now, you could be more demanding and say, what about the individual components? Can you also say something interesting about each component? Now, this is a priori not a well-defined problem because you're free to choose any basis. But there is a preferred basis, and that's what I said earlier. We can take the Wigner basis. This is a very natural basis because it's also a basis of eigenfunctions with respect to the action of diagonal matrices. So it's certainly a very natural basis, and every physicist would immediately agree that this is the basis you should choose. Now, once you have fixed your basis, now the question again, can you bound the individual components? So not just the vector, but each fj. Again, the trivial bound would be k. And the second theorem, again, with the same collaborators, is that regardless what entry you choose, for any m, you save a little bit, 1/27. And this 1/27 is not optimized. There is no significance about the number 27. It's just to give you a concrete number. If we worked harder, we could probably improve this exponent. Yeah, but it's a strictly positive saving. And the interesting fact is that for some indices, you can actually do much better. If you take the most outside, the most extreme cases, so the indices minus k and plus k at the edge of the vector, then you can save really a lot. If you are not an analytic number theorist, you may not be interested in certain exponents. But if you happen to be an analytic number theorist, then you are interested in numerically strong savings. And I mean, the trivial bound is k, and getting all the way down to square root k is numerically a lot. Okay, but this is only available for these two outside vectors. All right, and yeah, this is a long paper. I cannot give you details of the proof. It uses the most advanced technology to actually, well, get to this 1/2. Let me summarize by recalling that the beauty of the sup-norm problem, as I presented it in this lecture, is that it takes mathematics from very different areas. It starts as a purely analytic problem. Then it uses number theory once you pass to arithmetic manifolds. It needs a lot of analysis on Lie groups, and it also needs a lot of representation theory. And all of these areas play together to bound the sup-norm of joint eigenfunctions. And as we have seen on some other slide, this can be used actually in applications. All right, that's all I wanted to say. And I'm happy to answer all questions you might have.
So is there any questions here? Yes. So one question.
Hi, sir. I hope you can hear me.
Yes.
So I guess all the instance of the theorems that you gave, you showed it for SL to see your SLN or GLN, all the standard Lie groups. What if you go beyond them? Like,
That's a very interesting question. Very good question. Thank you. Right. So most of the work has been done for SLN, GLN. There is also some work on symplectic groups, by okay. Then so it's Das and someone else whose name slips my memory. But there is a nice paper on SP4, and there is also a student of Jörg Kramer who did the SP4 case, and he has also some work on SP2N. So the symplectic case is well studied, or it's at least studied to some extent. And it's in many aspects similar, but in some other aspects also quite a bit harder. Yeah, so the symplectic groups have been studied. I don't know of papers. Okay, there is a paper by Simon Marshall, which is at least available on arXiv, but to my knowledge has never appeared in print anywhere. He studies quite generally groups, satisfying certain technical assumptions. So there has been some work on other groups, but it doesn't exhaust all the groups. There are always some assumptions, and there is certainly a lot of things that can be done, and there is a lot of work to do.
Okay, so thank you.
Is there any other question? So if it not depends. Any question? The people who can unmute them.